Hi, are you still there?
Students from math, you still there? It looks like, but
What?
we have a few questions for the math students.
Okay.
Right. So I was wondering how often you do MATH.en.JEANS. Do you do it once per month or once per week?
Once per week.
Once per week. Cool. So does anyone have a question? Yes, please.
Yeah, thank you very much for the presentation. Have you thought about changing the procedure from the beginning, so instead of subtracting one part and like from going away from this problem that you have, perhaps taking more or like different transformations of the couples and trying similar strategies?
Did you hear the question?
No.
So his question was, if I've understood correctly, why you didn't choose other procedures?
Okay, so can you hear me?
Can you hear him? Yeah, just.
Yes.
Okay, so perfect. So you've got this very nice problem with the squirrel that you solved, and you have this transformation on the couples AB transforming to 2A and B minus A. Have you thought about taking other transformations on the couples, like, I don't know, multiplying by 3 and taking B minus 2A, for example? Do you think that similar strategies can work?
Did you hear the question?
Yes, I heard.
Yeah, so he basically asked about whether you could have used different transformations for your couples, the ones that you mentioned in the beginning, and yeah. Hello. I think we've lost them again. They're not there anymore.
Yeah, it's short answers. Okay, so we're gonna go to the next presentation, and next presentation will be from a group of Yash, and it's called about a remarkable number. So Yash. I think we lost them as well. Oh no, they're here. Okay. Yash, you have the right to be a presentation. You can download yours and start whenever you want.
Hello, can you hear us?
Yes, we do.
Yes.
Okay, good. So, hello, we're going to present a problem called remarkable numbers. We are Avurvări Maria, Claudia,
Andrei, and Alex.
We are from the National College Iași, Romania. This is our first time participating in the MATH.en.JEANS workshop, and now we're going to start our presentation.
The problem. A number is called remarkable if there exists a multiple of it
that is written in the 10th place as a string of the digit 9, followed or not by a string of the digit 0. For example, we had to answer if the number 3 is remarkable and to justify why it is or it isn't. We also had to answer what are the remarkable numbers lower than 6 and what are the remarkable numbers in general. As a mathematical definition, an integer x other than 0 is called remarkable if there exists a multiple of it noted with mx as a string of the number 9 multiple of times, then the digit 0 multiple of times, or the string of the digit 0 can also be inexistent.
So, is 3 a remarkable number and why? 3 is a remarkable number because there exists a multiple of 3. 3 times 3 equals 9, with m equals 1 and n equals 0. 2. Which numbers smaller than 6 are remarkable? The remarkable numbers that are smaller than 6 can be divided into categories: positive integers and negative integers. Which numbers smaller than 6 are remarkable? 1, 2, 3, 4, and 5 are remarkable numbers because there exists multiple of 1. 1 times 9 equals 9, with m is 1 and n is 0. Multiple of 2. 2 times 45 equals 90, with m equals 1 and n equals 1. Multiple of 3. 3 times 3 equals 9, with m equals 1 and n equals 0. Multiple of 4. 4 times 225 equals 900, with m equals 1 and n equals 2. Multiple of 5. 5 times 18 equals 90, with m equals 1 and n equals 1. Note that the specified multiples are not unique. To determine all negative integers that are remarkable numbers, the general form of the remarkable positive numbers will be determined later.
3. In general, which numbers are remarkable? All positive integers are remarkable numbers. Proof. We will prove that any positive integer x has a multiple of form 999 taken of m times, followed by 000 taken of n times, with m and n unspecified. Remark 1. Finding x, an integer x different from 0, remarkable, for which there exists a multiple with the form a multiple of x equals 999 taken of m times and 000 taken of n times. That equals 9 multiplied by 111 taken of m times, multiplied by 2 to the power of n, multiplied by 5 to the power of n, with n a positive integer and n a positive integer. Is like looking for the divisors of the number 9 multiplied by 111 taken of m times, multiplied by 2 to the power of n, multiplied by 5 to the power of n, using the divisibility criteria in number theory.
Statement 1. For all n1 numbers which are natural, all n2 numbers which are natural, and all s numbers which are natural, the numbers 2 to the power of n1 multiplied by 5 to the power of n2 multiplied by 3 to the power of s are remarkable numbers. Proof.
Sorry, excuse me. There is a problem with the presentation. We only set a slide from the beginning.
Sorry, excuse us, we can't hear you too well. If you could repeat what you just said.
We had a problem with the presentation. We only see the first slide.
Can you write in the chat, please? That's not good.
probleme cu slide-urile. Nu au văzut decât primul slide. Ați dat slide-uri? Hai să ne întoarcem.
Să știți că nu s-a scris înainte de să ștergeți. Stop sharing.
Hai.
Și acum începeți din nou.
Hai, din nou.
Nu, e ok.
Dar ce aveți tot timpul în față? Orice. Nu începeți din nou. Ce ne-ați urmat. Ok.
Și dau share? Da? Și share sistem audio?
Can you see now the other slides?
Yes, perfect.
Okay. Should we start from the beginning or should we continue?
Maybe you can have like a quick resume from the beginning.
Yeah, sure. We will do a quick recap right now. Okay, so we will start again from the problem.
So, the problem, a number is called remarkable if there exists a multiple of it that is written in the 10th base as a string of the digit 9, followed or not by a string of the digit 0. And for example, we had to answer if the number 3 is a remarkable number, and to justify why it is or it isn't. We also had to answer if what are all the numbers lower than 6. And lastly, we had to answer what are the remarkable numbers in general. And as a more mathematical definition, an integer x other than 0 is called remarkable if there exists a multiple of it noted with mx that can be written as the digit 9 multiple times, followed by the digit 0 multiple times.
So the first question is 3 is a remarkable number, and why? 3 is a remarkable number because there exists a multiple of 3 times 3 equals 9 with m where is 1 and n is 0. And which numbers smaller than 6 are remarkable? The remarkable numbers that are smaller than 6 can be divided into categories: positive integers, 1, 2, 3, 4, and 5, and negative integers. Which numbers smaller than 6 are remarkable? 1, 2, 3, 4, and 5 are remarkable numbers because exists a multiple of 1 times 9 equals 9 with m where is 1 and n is 0. Multiple of 2 times 45 equals 90 with m1 and n1. Multiple of 3 times 3 equals 9 with m is 1 and n is 0. Multiple of 4 times 225 equals 900 with m1 and n2. And multiple 5 times 18 equals 90 with m equals 1 and n equals 1. Note that the specified multiples are not unique. To determine all negative integers that are remarkable numbers, the general form of the remarkable positive numbers will be determined later.
Now, which numbers are remarkable? All positive integers are remarkable numbers. Proof. We will prove that any positive integer x has a multiple of form 999 taken of m times, followed by 000 taken of n times, with m and n unspecified. Remark 1. Finding x, an integer, with x different from 0, remarkable, for which there exists a multiple with the form multiple of x equals 999 taken of m times, followed by 000 taken of n times, equals 9 multiplied by 111 taken m times, multiplied by 2 to the power of n, multiplied with 5 to the power of n, with m an a positive integer and n a positive integer. It's looking for the divisors of the number 9 multiplied by 111 taken to the power with m, multiplied by 2 to the power of n, multiplied with 5 to the power of n, using the divisibility criteria in number theory.
Statement 1. For all n1 numbers which are natural, all n2 numbers which are unnatural, and all s numbers which are natural, the numbers 2 to the power of n1 multiplied by 5 to the power of n2 multiplied by 3 to the power of s are remarkable numbers. The proof is for all n numbers which are natural, there exists mn equals 1, 1, 1 taken m times, multiplied by 9, multiplied by 2 to the power of n, multiplied by 5 to the power of n, which is a multiple of 2 to the power of n, multiplied by 5 to the power of n. And out of our curiosity, we used the scientific workplace program for the decomposition into prime factors for 1, 1, 1 taken m times, for m between 1 and 81. Here are some of the examples. Some of the more notable ones are m equals to 19, which is prime, with m equals to 23, which is prime, and which will also be some of the prime factors. And when m equals 71, the scientific workplace program did not work. And when it was 73, also didn't work, probably because of the big number of prime factors.
Heuristic 1. For all s, which s is a positive integer, the number 3 to the power of s divides 111 taken 3 to the power of s times. Using mathematical induction, we will prove the divisibility statement. Let Ps be a proposition which states that 3 to the power of s divides 111 taken 3 to the power of s times for all s positive integers. Obviously, P1 is true, that is the basic step, because 3 to the power of 1 divides 111, which is 3 multiplied by 37. So, in the next step, we can assume that Pk, which states that 3 to the power of k divides 111 taken 3 to the power of k times for all k positive integers. Then there exists d, a positive integer, such that 111 taken 3 to the power of k times can be written as 2 as d multiplied to 3 to the power of k. Let us prove that p of k plus 1 is true. That is the induction step. P, k plus 1, states that 3 to the power of k plus 1 divides 111 taken as 3 to the power of k plus 1 times. We observe that the number 111 taken 3 to the power of k plus 1 times can be written as 111 taken to 3 to the power of k times. 3 times, obviously. So we can write it as d multiplied by 3 to the power of k, multiplied by 10 to the power of 3 to the power of k, multiplied by 10 to the power of 3 to the power of k, plus d multiplied by 3 to the power of k, multiplied by 10 to the power of 3 to the power of k, plus d multiplied by 3 to the power of k, multiplied by 1. So if we take out the common factor, we obtain that d multiplied by 3 to the power of k, multiplied by 10 to the power of 3 to the power of k, multiplied by 10 to the power of 3 to the power of k, plus 10 to the power of 3 to the power of k plus 1 is the actual remainder. Using the rule of divisibility by 3, since the sum of the digits for that number is 3, we obtain that there exists d prime, a positive integer, such that that number is divisible by 3, and we can write it as d prime multiplied by 3. Then there exists d multiplied by d prime, a positive integer, such that 111 taken 3 to the power of k plus 1 times is d multiplied by d prime multiplied by 3 to the power of k plus 1. So we proved what we wanted to prove, that 3 to the power of k plus 1 times divides 111 taken to 3 to the power of k plus 1 times for all k positive integers. So the induction is complete, and by the principle of mathematical induction, the statement is true for all positive integers.
Okay, now the second statement. All prime natural numbers greater than 5 are remarkable numbers. We verify that every prime number greater than 5 and lower than 100, 7, 11, 13, and so on, is a remarkable number because x divides the digit 1 a number of times with m that's not unique. And here we got some examples. For instance, for the number 7, we have more than 10 examples to prove that the number 7 is a remarkable number. As for numbers such as 97 or 61, we've only found one example, but they're still remarkable numbers.
Okay, then we wrote the number 111 taken m times as the sum of 10 to the power m minus 1 plus 10 to the power m minus 2, so on, plus 10 to the power 2 plus 10 to the power 1 and plus 10 to the power 0. And we will analyze a few examples so that we can find the rule to write m depending on prime number with p bigger than 5 such that p divides 111 taken n times. For example, p equals 19. When we divide the powers of 10 by p, we will obtain the following remainders. For 10 to the power 0 with 1, for 10 to the power 1 is 10, and so on. And then we made the sum of them and observe that is a multiple of 19. So m, the numbers of 1 in the first number, is a multiple of 18. We take another example, p equals 7. When we divide the powers of 10 by 7, we will obtain the following remainders. For 10 to the power 0 is 1, for 10 to the power 1 is 3, and so on. And then again we made the sum of them and observe that it is a multiple of 7. So m is a multiple of 6. And we repeat this process for other examples. And at the end, it can be assumed that in general, m is a multiple of p minus 1.
Our third statement is that for all alpha positive integer and all prime numbers p positive integer that is different from 0 with p greater than 5, the numbers p to the power of alpha are remarkable numbers. As my colleague previously said, we try to decompose 1111 written m times to a sum of the powers of 10. And so we have the sum is 10 to the power of m minus 1 plus 10 to the power of m minus 2 and so on till we get to the 10 to the power of 1 and finally 1. We try to demonstrate that a prime number p to the power of 2 is a remarkable number for any p greater than 5. And as our example, we took p equals 7, and thus 7 to the power of 2 is 49. And we applied the same rule as before. With our program, we tried to find the reminders. And what's curious about this case is that the reminders repeat themselves every 40 times, which can be written as 7 multiplied by 6, or as a p form, p multiplied by p minus 1. And using our program again and again to find for other prime numbers such as 11 and 13, we found out that our intuition is right and we obtained the same rule. So we said that p to the power of 2 divides 111 written p to the power multiplied by p minus 1 times. And with this, we had some kind of intuition that p to the power of 3 might somehow divide 111 written p to the power of 2 multiplied by p minus 1 times. And again, with our program and doing experiments and analyzing cases, we found that that is true. And by the last 3 things that we presented, we concluded that any p prime number greater than 5 at the power alpha, that is the positive integer different from 0, divides 1 written p to the power of alpha minus 1 multiplied by p minus 1 times. And thus we found out that the power of prime numbers are remarkable.
Okay, statement 4, for any a1, a2, and so on, k positive integers, and any prime number p1, p2, and so on, pk, greater than 5, the numbers p1 to the power a1 multiplied by p2 to the power a2 multiplied by so on, multiplied by pn to the power an are remarkable numbers. So we found out that this is true because using what we found here, that p to the power a divides 111, taken a multiple of p to the power a minus 1 multiplied by p minus 1. And because the numbers are prime, that means that if p1 to the power a1, p2 to the power a2, and so on, pn to the power an, divide the 111 taken a multiple of p1 to the power a1 minus 1 multiplied by p1 minus 1 multiplied by p2 to the power a2 minus 1 multiplied by p2 minus 1, and so on, multiplied by pn to the power an minus 1 and multiplied by pn minus 1. That means the product of these numbers divides 111 taken this multiple of this number. And now we have a conclusion. In conclusion, after analyzing all the possible cases, we can see that every integer, positive or negative, is a remarkable number because we were able to find a multiple of it written as a string of 9, followed or not by a string of 0. Thank you for your attention.
So do you have any questions that we might be able to answer them? We are not able to hear you if you are saying anything.
Bonjour à tous. Aujourd'hui, le lycée français et l'école européenne vont vous présenter nos recherches sur le thème des jeux tic-tac-toe, Hachi et Picaria. Nous allons essayer de répondre à la question que chaque élève s'est déjà posée un jour. Est-il possible de gagner à tous les coups? Et si oui, comment? Je suis certaine que la majorité d'entre vous a déjà joué à ce jeu. Mais pour les autres, voici les règles. Le tic-tac-toe, aussi appelé morpion et oxo en Belgique, est un jeu de réflexion se pratiquant à 2 joueurs dont le but est d'être le premier à créer un alignement de 3 symboles identiques.
Nous avons donc réfléchi à une stratégie qui fonctionnerait sous forme d'algorithme et qui nous permettrait de gagner à tous les coups. Les 2 premières étapes étaient placer un pion gagnant, donc pas de hasard après 2 tours, et ou bloquer l'adversaire, donc empêcher l'adversaire de mettre un point gagnant. Mais que faire lorsqu'on se trouve dans aucune des situations? Placer un pion aléatoirement, c'est une possibilité, mais ce n'est pas la solution la plus fiable. Pour cela, nous avons commencé par créer un système de points. Au début de la partie, toutes les cases ont un score de 0. Lorsqu'un pion est placé, toutes les cases se trouvant sur la même ligne, colonne ou diagonale gagnent un point. On peut donc voir quelle case nous ouvre le plus de possibilités de gagner.
Lorsqu'un pion est placé sur une case, celle-ci perd tous ses points. Ici, on voit que le joueur rouge a posé son pion sur la case F. En tant que joueur bleu, il va falloir qu'on place notre pion de manière à avoir le plus de chances à la suite de pouvoir gagner. Donc pour cela, il faudrait mettre son pion à un endroit qui permettrait de placer un point à la suite sur le plus de cases possible. Ensuite, il faudrait essayer d'embêter notre adversaire et pour ce faire, il faudrait mettre son pion à un endroit où le joueur adversaire, donc le joueur rouge, a déjà des points, un ou plusieurs points. On peut répéter cette opération jusqu'à ce que 4 cases soient occupées, car à la suite, assez souvent, on peut se raccrocher aux 2 premières étapes de la stratégie qui sont placer un point gagnant ou bloquer l'adversaire. Ici, il y a un cas un peu spécial parce qu'on peut voir que le joueur rouge possède une case avec 2 points. Cependant, il n'a pas 2 pions alignés sur l'une des lignes reliées à cela. Cela veut dire pour le joueur bleu que le joueur rouge risque de le mettre en position d'échec et mat. Et donc, pour empêcher cela, il faut placer son pion sur la case avec les 2 points, donc la case C.
Mais cette stratégie n'est pas parfaite. Il y a une exception ici, qui est ce cas de figure. Dans ce cas de figure, on peut voir que le joueur A rouge, il y a donc 2 cases avec un score de 2. Si le joueur bleu allait appliquer la tactique précédente, il devrait bloquer sur 2 fronts, ce qui est impossible. Il va donc falloir placer son pion sur les cases B, F, H et D pour forcer le joueur A, qui est son adversaire, à bloquer le joueur bleu et éviter qu'il puisse placer son point gagnant.
Au début de nos recherches, nous voulions faire un système de valeurs attribuées à chaque case et on a commencé par faire un arbre des possibles. On s'est rendu compte que lors du premier tour, si on commence sur le coin, l'adversaire peut choisir entre 8 cases et 7 de ces cases nous mènent à la victoire. De même, si on commence sur le milieu ou le côté, on a une chance sur 2 que l'adversaire choisisse une case qui nous mène à la victoire. Le coin maximise donc nos chances de gagner. Mais finalement, on se rend compte que c'est peut-être plus intéressant de tout simplement créer une stratégie à partir des coins, et de ne pas faire une intelligence artificielle qui évalue toutes les possibilités.
En parallèle, on s'est rendu compte que 3 pions sur la grille peuvent former 2 lignes, où il nous manque une case pour gagner. À ce moment-là, notre victoire est garantie, car l'adversaire ne peut pas nous bloquer à 2 endroits en même temps. C'est le pilier de notre stratégie au morpion. On essaye d'atteindre cette configuration pour maximiser nos chances de gagner. Il existe également une deuxième configuration, où les 3 pions forment 3 lignes. Cette configuration est optimale. En effet, on peut se permettre de sacrifier une ligne pour manipuler l'adversaire pendant la partie. Selon nous, peu importe la stratégie, il faut commencer par jouer au coin. En effet, c'est la case qui maximise nos chances selon l'arbre de possibilités, et on s'est également rendu compte que toutes les configurations de 3 pions passent par le coin. Ensuite, il faut repérer un ensemble de 3 points qui forment 3 lignes, dont aucune des cases ne passe par la case de l'adversaire. Et ça, on peut facilement le voir visuellement par un triangle. Ensuite, il faut repérer la case sur laquelle on va d'abord jouer, et il faut s'assurer que ça ne renforce pas une ligne où l'adversaire peut gagner. Ici, on voit qu'on ne peut pas jouer en bas à droite, mais qu'on peut jouer en haut à gauche. Désormais, il ne reste plus qu'à placer le 3e pion qui complète l'ensemble de cases pour gagner la partie.
Cependant, notre stratégie pour créer une configuration forcément gagnante n'est pas infaillible non plus. En effet, si l'adversaire joue au milieu, il est impossible de créer une configuration optimale puisqu'elle passe tous par le centre. Il ne reste plus qu'à essayer de gagner en créant une configuration à 2 lignes. Nous avons maintenant aussi écrit un programme Python pour créer une intelligence artificielle qui utilise notre stratégie. Et donc, sous vos yeux, vous pouvez voir le logigramme qui montre ce que fait notre algorithme. Donc, pourquoi on a fait un programme? Donc, déjà pour vérifier que notre stratégie marche et aussi pour apprendre à coder en Python. Donc, la différence avec notre stratégie initiale, c'est que si on devait regarder chaque ensemble de 3 points tout au long de la partie, cela prendrait beaucoup de code et serait beaucoup moins performant. Et on s'est rendu compte qu'on pouvait créer des configurations à 3 points optimales qui passent seulement par des coins. Et donc, on a simplifié le programme pour qu'il ne regarde que ces ensembles-là.
Comme le tic-tac-toe, le hachi est un jeu d'alignement qui se joue à 2. Le but est d'aligner 3 symboles identiques. Ce qui le différencie du tic-tac-toe, c'est le fait qu'une fois les jetons déposés sur le plateau, il est possible de les bouger afin d'obtenir un alignement.
Au terme de notre recherche, nous avons pu élaborer une stratégie qui permet de gagner au hachis. Nous allons d'abord commencer par expliquer le passage du tic-tac-toe au hachis. Nous avons essayé plusieurs possibilités de déplacement au tic-tac-toe pour trouver des positions gagnantes ainsi que des positions perdantes, qui nous ont permis de progresser vers l'objectif initial de trouver une stratégie pour le hachis. Le rond, en commençant en coin, a le plus de chances de gagner au tic-tac-toe et donc on ne peut plus poursuivre avec le hachis. Pour pouvoir jouer au hachis, il faut qu'il y ait égalité et cela suppose alors d'éliminer la position gagnante au tic-tac-toe qui consisterait à commencer au coin. À droite, nous pouvons voir un des exemples qui mène à l'égalité au tic-tac-toe bien qu'on ait commencé au coin. Si au début de la partie le rond se trouve dans la case du coin, au hachis c'est une défaite assurée. Nous avons testé notre théorie à plusieurs reprises et c'était toujours le cas. Ensuite, nous pouvons voir que l'étape suivante pour le rond sera de se déplacer, et dans une telle configuration, il n'a que deux possibilités de mouvement. Ici, nous pouvons voir que le rond peut occuper les dernières cases libres en y arrivant de deux façons différentes. Soit on libère la case de droite, soit celle du côté gauche. Si le rond quitte la case 5, la croix gagne directement en complétant l'ensemble des trois cases à l'horizontale. Cela signifie que la seule possibilité qui resteront, c'est de se déplacer de gauche à droite. Si nous considérons que le joueur qui joue avec les croix est un bon joueur, il va sûrement prévoir les prochains mouvements de l'adversaire et donc déplacer la croix sur le côté pour limiter le nombre de coups et de possibilités du rond. On arrive maintenant à une configuration où les ronds n'ont aucune possibilité de gagner. Peu importe leur prochain coup, les croix gagnent. Au cours de l'étape suivante, la croix se déplaçant dans le coin, il y a un alignement en diagonale des croix qui gagne ainsi la partie. Et enfin, les croix sont dans une position gagnante en s'alignant. Cela confirme la théorie selon laquelle le premier joueur qui se met dans le coin, soit il gagne au tic-tac-toe et le jeu s'arrête, soit il arrive à égalité à la fin du tic-tac-toe et perd au hachis.
Après avoir vu qu'utiliser la méthode qui nous permet d'avoir le plus de chances de gagner au tic-tac-toe ne marche pas au hachis, nous avons essayé d'autres positions de départ. Et en nous concentrant sur le hachis et les stratégies qui permettent de gagner à tous les coups, nous avons trouvé une stratégie qui fait gagner celui qui commence à tous les coups. Nous avons trouvé une position qui, à la fin du tic-tac-toe, fait remporter celui qui est dans cette position. C'est une forme géométrique en forme de Y, et on peut, comme vous pouvez le voir dans les exemples. Et on peut, pour celui qui commence, avec une méthode très facile, y parvenir à tous les coups. Il suffit de manipuler et contrôler chaque étape du jeu en obligeant l'adversaire à se déplacer là où c'est le plus avantageux pour le joueur jouant avec les ronds. Nous allons montrer un exemple qui illustre bien cette méthode. Et tout d'abord, toute manipulation doit commencer par le centre. De cette façon, quand on arrive au hachis, on aura une possibilité de plus pour se positionner sur la case libre, comme on verra tout à l'heure. Les numéros en dessous de la case correspondante. Les numéros en dessous de la case correspondent à l'ordre des coups joués. En utilisant la méthode qu'on va montrer dans un instant, le premier joueur gagne à tous les coups. Dans ce cas, le deuxième joueur va jouer dans un coin, car sinon il perd au tic-tac-toe, et dans ce cas, il joue en haut à droite. Puis, le rond, en suivant la méthode, va mettre son pion dans un endroit pour que l'adversaire ne puisse pas choisir l'emplacement, dans ce cas, au milieu à droite. En continuant d'utiliser cette méthode, on va arriver à la position Y. Si vous pouvez directement passer à la conclusion. Et donc, en étant dans cette position d'Y, le premier joueur va automatiquement gagner. On a également remarqué qu'en testant plusieurs combinaisons, que plus on aura de possibilités de déplacement, plus sa victoire sera probable dans n'importe quelle position. C'est-à-dire qu'il ne faut jamais laisser plus d'une ou maximum deux possibilités en fin de partie aux croix de se positionner si les ronds veulent gagner.
Très vite, on s'est rendu compte que si on prend le contrôle du milieu au début de la partie, l'adversaire ne peut plus gagner. En fin de partie, les pions tournent autour du pion central jusqu'à ce que 3 de nos pions soient alignés. C'est le pilier de notre stratégie au hachis. Donc, on commence donc par jouer au milieu, au centre. Ensuite, on joue dans le sens horaire ou anti-horaire par rapport à l'adversaire. En fait, peu importe le sens, tant que vous gardez le même tout au long de la partie. Donc là, on va jouer à droite de l'adversaire. Et de cette manière, on aligne 2 pions et l'adversaire est obligé de nous bloquer. Ainsi, le processus se répète, on joue au sens horaire et donc on arrive jusqu'à la deuxième phase, la phase de déplacement. Mais souvenez-vous, on ne déplace pas notre point central, car de cette manière, l'adversaire n'a mis jamais 3 pions. On déplace alors le seul pion que l'on peut déplacer, le joueur adverse suit, et au bout de 2 déplacements, on a gagné. Les 3 pions du joueur 1 sont alignés.
Et pourquoi ça marche? Parce que par symétrie, lorsqu'on commence par jouer au centre, l'adversaire n'a en réalité que 2 possibilités, soit jouer dans un coin, soit jouer sur le côté. Et lorsqu'on joue toujours sur la carte entre guillemets suivant dans le sens horaire ou anti-horaire, seulement 2 patterns possibles arrivent à la fin de la partie, et ces 2 patterns nous permettent tous les deux de gagner. Et donc cette méthode, même si elle est simple, nous permet toujours de gagner.
Le Picaria est un jeu de stratégie abstrait à 2 joueurs. Il est lié au tic-tac-toe mais ressemble plus au hachi, car les pièces peuvent être déplacées pour créer le 3 en ligne. Le Picaria est un jeu d'alignement, mais contrairement au hachi ou au tic-tac-toe, les joueurs ne peuvent pas placer un pion au centre de la grille, donc tous les pions ont été placés. Il existe 2 variantes du Picaria. La première version est plus simple avec 9 espaces ou points d'intersection, et la seconde version utilise 13 espaces ou points d'intersection.
Ensuite, on va avoir une première approche où notre stratégie va être d'ouvrir le plus de possibilités possibles pour gagner. Gagner en déplaçant un de nos pions vers le centre et puis terminer la partie avec le moins de tours possible. Ces stratégies ressemblent beaucoup à celles du morpion.
Donc, on va placer le premier pion sur la gauche pour ouvrir le plus de possibilités, car on ne peut pas commencer par le centre au Picaria. Donc, l'adversaire peut placer son pion n'importe où et c'est de nouveau à nous de jouer. On place le second pion au centre du carré en bas à gauche pour former une première opportunité de victoire. Et si l'adversaire le repère, il va être contraint de bloquer. C'est encore à nous de jouer et on va se mettre en position de triangle pour avoir la possibilité de déplacer son dernier pion vers le centre. Donc le pion initial, il va se déplacer vers le centre et la victoire sera à nous.
Donc, pour le Picaria, on réutilise la stratégie du morpion, qui consiste à trouver une configuration en 3 points, qui forme 3 lignes sur la grille. Toutefois, on ne peut utiliser que 3 pions. Donc, pour compléter la ligne à la fin de la partie, il faut que l'on déplace un pion déjà placé, modélisé par la flèche verte. De plus, cette ligne doit passer par le milieu. De cette manière, l'adversaire ne peut pas nous bloquer sur la ligne où on compte à gagner. Il existe plusieurs configurations qui répondent à ces critères. On retrouve bien la configuration du groupe précédent. Au premier tour, il est optimal de jouer au milieu d'un des côtés du carré. En effet, c'est la case par laquelle passe le plus grand nombre de configurations en 3 points. Il faut repérer un ensemble de 3 pions qui forment 3 lignes, dont aucune de ces lignes ne passe par une case de l'adversaire. On voit aussi qu'une des cases peut être déplacée pour former la ligne à la fin de la partie. Il faut s'assurer que l'adversaire sera obligé de nous bloquer après avoir placé un pion. Il faut également s'assurer que la case où l'on imagine que l'adversaire va jouer ne renforce pas une de ces lignes, comme pour le morpion. Ici, on est obligé de jouer sur la case de droite. Comme prévu, l'adversaire nous a bloqués. On peut désormais compléter l'ensemble de 3 cases. Peu importe où joue l'adversaire, il ne reste plus qu'à déplacer la dernière case pour aligner les 3 pions. On a ainsi remporté la victoire. Peu importe où joue l'adversaire au début, il existe forcément une configuration de pions qui permet de gagner au Picaria, contrairement au morpion. Ainsi, on peut garantir notre victoire.
We have developed a method in which the first player will always win at Picaria. For the first player, the main goal is trying to stay as close as possible to the middle, as this will open the most options to get 3 in a row, and therefore the second player has to try to lure the first away from the middle. We have represented the first player with the white tiles and the second with the black tiles, and the numbers indicate the order in which each tile is placed. In the next few slides, we're going to try to explain our approach to you by every step we took.
This is the method we came up with. We will now show why we placed each tile accordingly and the reasoning behind the movements.
For the placement of the first tile, there are 12 options. However, due to the symmetry of the board, ultimately there are 3. Those would be the outer corners, the middle of the outer lines, and the inner parts of the board.
Instead of explaining why each of these would be inefficient, we're simply going to explain why we believe that the inner part of the board is the best option for the first player. As you can see in the top two diagrams, given that the first player places on the inner part of the board, no matter what the second player does, the first player can place in the top left corner, and therefore, by placing any position that has access to the middle with the third tile, win in one move. This wouldn't work if the second player places in the corner. And as you can see in the third diagram, the first player would have to block, and therefore the second player can create a perfect win situation by either removing the first or second tile up. This can be blocked the way is represented in the fourth diagram, and therefore the most efficient move for the first tile of the second player would be in the top left corner behind the first tile.
This slide will be explaining how we place the second white tile. Given the symmetry, there are 6 options, either on the inside. These would drive white away from the middle and therefore drag out the game. This leaves options away from the action in the middle parts of the outer lines, which would have a similar effect as it would spread out the tiles over the board, again dragging the game out unnecessarily. The fourth and fifth options are placing on corners. Again, the game would last longer than needed. This only leaves the most efficient way, as close to the action as possible.
Placing on either of the places demonstrated in the previous slide would make the following 2 moves mandatory blocks, since the game would end without them. Black would have to block, as shown in the first diagram, and in turn, white would have to block, as shown in the second.
This brings us to the placement of the final tile. If the player places its tile in the top right corner, white could win in 2 simple moves. This cannot be blocked by black, nor can black get 3 in a row beforehand. Most other positions would give white a similar opportunity. The only way this wouldn't work is if the bottom 4 places are used. If these placements are used with different moves, they would all end up in similar positions, making placing in the middle of the bottom line the most efficient.
To show you how this placement would play out, we have created this tree diagram. The second player has the option of moving their first or second tile, giving it 3 possible movements. The purple branch at the top shows how moving the first tile would end. The green in the middle shows how moving the second tile upwards would end, and blue at the bottom shows the way the movement of the second tile downward would result. As you can see, in each of them, player 1 always wins.
And this brings us to our final step-by-step method, as you can see. In this presentation, we have shown the most efficient game possible. In this case, white will win. If player 2 wants to win, they would have to drag the game out as much as possible, making the moves less efficient. This would give white more opportunities to make mistakes and leave an opening for black to win.
En conclusion, on observe que plus le jeu est complexe, plus les méthodes pour gagner sont efficaces. Pour le morpion, qui est censé être le jeu le plus simple, on a seulement pu maximiser nos possibilités de gagner, alors que pour le Hachi, le Picaria, on a pu trouver des méthodes qui nous permettent de gagner à coup sûr.
Okay, so this is my code, and for the game tic-tac-toe, and you can play it with your friend or anybody else. And I will quickly explain the code. So the first image, the one on the left, it makes like the board. So yeah, it stores the board, and also it has the algorithm to check for if somebody won. And the second image, the one on the right, is like the actual game and like lets you place a piece and move and whatever. And right now I'm working on a bot to beat you and to always win or tie.
L'une des solutions que nous avons trouvées pour Hachi était de faire un arbre de décision. Ici, les nœuds verts représentent les victoires du premier joueur et les nœuds rouges, les victoires du second. Il y a également des nœuds blancs dans lesquels aucun des joueurs ne gagne. Les liens sont également attribués à certains joueurs. Lorsqu'on est le joueur rouge, on ne peut suivre que les liens rouges. Ainsi, vous pouvez trouver toutes les possibilités et solutions pour chaque partie que vous jouerez. Cependant, pas sûr que ce soit la partie la plus rapide de votre vie.
Nous ne voulions pas seulement nous contenter d'utiliser une stratégie qui est seulement un tenté. Nous voulions aussi regarder le futur pour pouvoir avoir une stratégie plus générale qui fonctionnerait avec tous les jeux. Pour cela, il fallait qu'on simule le jeu de l'adversaire. Ensuite, à partir de ce jeu de l'adversaire, il fallait trouver une réponse adaptée pour éviter que l'adversaire puisse gagner. Ensuite, pourquoi s'arrêter au jeu de l'adversaire et trouver une réponse là? On peut très bien répéter ces étapes et resimuler le jeu de l'adversaire pour trouver la réponse la plus adaptée depuis la fin du jeu. Et il se trouve que cet algorithme existe déjà.
Donc, comme Tom a dit, cet algorithme existe déjà et il est connu sous le nom de l'algorithme Minimax. Et il a été développé par John von Neumann en 1928. Donc, c'est un mathématicien et un physicien anglo-américain, pardon. Et il est considéré comme le père de la théorie des jeux parce qu'il a beaucoup développé ce domaine et il était même un des fondateurs principaux.
Alors, cet algorithme se base sur un arbre du jeu. Il va créer, à partir d'un état initial, toutes les possibilités futures. Ensuite, à la fin du jeu, il va évaluer le jeu. Il va lui attribuer un score en fonction de qui a gagné. Par exemple, une victoire du robot va être 10 points ou une défaite du robot va être moins 10 points. Ensuite, on va remonter cet arbre en prenant soit le score minimal, soit le score maximal. Et à la fin, on va jouer le coup qui donnera le score maximal, afin de maximiser nos chances de gagner. Nous avons deux systèmes pour le contrôler. Déjà, on peut adapter la notation. Par exemple, donner plus de points à une victoire dans une colonne pour favoriser les victoires dans les colonnes. Mais on peut aussi modifier la profondeur de recherche, c'est-à-dire la profondeur dans laquelle le robot va s'avancer dans le jeu, le nombre de coups d'avance que le robot va avoir sur le joueur.
Donc, le résultat de cet algorithme Minimax adapté aux 3 jeux qu'on a observés sont au tic-tac-toe, si les 2 joueurs jouent de façon optimale, ça finira toujours en égalité. Mais pour le Hachi et les Picaria, qui sont les jeux plus complexes, le résultat est plus intéressant car le joueur 1, s'il joue optimalement, peut toujours assurer la victoire. Alors, l'algorithme Minimax présente beaucoup d'avantages. Donc, premièrement, son concept basique est assez intuitif. C'est maximiser nos chances de gagner et minimiser les chances de l'adversaire. C'est aussi le moyen le plus efficace de jouer, et donc c'est la solution optimale. Et il est généralisable pour beaucoup de jeux, donc notamment les jeux comme les 3 qu'on a déjà vus, le puissance 4, les échecs, etc. Mais le Minimax présente aussi quelques inconvénients. Donc premièrement, c'est une forme de force brute, car l'algorithme doit vérifier toutes les possibilités et doit brancher. Et donc comme Tom a dit, il doit chercher dans un certain niveau de profondeur tous les moves possibles. Et donc à cause de cela, il nécessite beaucoup de RAM et de mémoire.
J'ai aussi implémenté cet algorithme en Python. Une particularité de cette implémentation est que j'effectue une boucle du minimax à l'extérieur de la fonction du minimax pour y sauvegarder le meilleur coup possible et éviter de devoir transférer le meilleur coup possible dans la branche du minimax. Cela permet d'économiser un tout petit peu de mémoire. Merci.
Avez-vous des questions? On ne peut pas vous entendre. On ne peut pas vous entendre. Vous n'avez pas de micro, je crois.
Est-ce que vous nous entendez?
Oui, oui, on vous entend.
Ah, super. Ok. Donc, on va vous reposer la question.
Ok. Est-ce que vous avez pensé à rajouter des optimisations comme alpha-beta pruning ou d'étape de transposition?
Je connaissais ces optimisations, mais je voulais pas les implémenter parce que je voulais avoir plutôt l'idée générale. Je voulais avoir une méthode générale pour qu'ils puissent résoudre le tic-tac-toe, le picaria et le hachi. C'était pas vraiment en termes de vitesse là encore. On pourrait regarder ça en regardant l'arbre du jeu. Ça serait pas trop compliqué à implémenter, mais on n'a pas eu le temps de le faire.
D'accord. Mais donc, ça veut dire que l'ordinateur peut calculer absolument toutes les positions de tic-tac-toe?
Pour le tic-tac-toe, il n'y a aucun problème. Pareil pour le hachi. Par contre, le picaria, il faut diminuer un peu la profondeur de recherche. Autrement, il est beaucoup trop lent. Mais il fonctionne.
Ah oui, d'accord. Donc, il n'y a pas besoin, en fait, d'optimisation.
Non, ça marche parfaitement, même en Python. Donc, c'est
D'accord.
très utilisable.
Ok, super. Merci.
Moi, j'ai une question d'ordre beaucoup plus général. On a toujours de superbes exposés d'intelligence artificielle qui viennent de l'AI. C'est des choix personnels, c'est ce qu'on vous propose, vous avez des cours.
Les sujets sont proposés par les chercheurs, donc c'est pas notre choix personnel et on fait pas de cours d'intelligence artificielle, mais c'est que c'est intéressant. Donc c'est bien qu'on puisse traiter ce genre de sujet.
En fait, on nous donne un choix, on nous donne certains exposés et après on choisit le projet qui nous intéresse le plus, mais on n'a pas énormément d'options non plus. Mais c'est un projet qui nous a tous intéressés, alors c'est pour ça qu'on l'a choisi.
Donc, on avait 6 options, on avait 3 options présentées par chaque chercheur. Et nous tous ici, on a trouvé que celui-là sur la stratégie des jeux, on l'a trouvé le plus intéressant, donc on l'a choisi.
Très bien. On est un tout petit peu en retard sur le planning, donc je vais vous laisser. Et on va donner la parole au prochain exposé. On vous remercie beaucoup. C'était super.
Merci, bonne journée.
Merci.
Au revoir.
Au revoir.
Au revoir.
Au revoir.
Le petit
Au revoir.
Au revoir.
We now have a group from Yash. Gabriel, you're the one with the right of presentation, is that right? Or should I give to the other person?
Could you repeat, please?
Which person I should give the right of having the presentation?
To us. To us,
Okay.
problem two. Thank you.
It's done.
Oh, 1 second. Can you see?
Yeah, it's perfect.
Okay, thank you. So we are the second team of National College of Yash, and we are Yulia,
Robert,
and Alexia, and we are going to show the equidecomposability of polygons. All right, so We will talk about problem statement, our solution, particular cases, and conclusions. Okay, so the statement is this. Two polygons A and B of equal area are given. Can polygon A be cut into smaller polygons that rearrange from polygon B? To make a reduction easier, we will use the following notations. A can be transformed into B, which means that A can be cut into smaller polygons which rearrange from B, and A cannot be transformed into B, which means that A cannot be cut into smaller polygons which rearrange from B. Example 1, we have A, a square width of side of 2, and B, a square with side 3, and A cannot be transformed into B. For the second example, we have A, a rectangle with sides of length 1 and 4, and B, a square with sides of length 2, and A can be transformed into B as shown in the pictures under. Okay, so here are some key observations. If A can be transformed into B, then B can also be transformed into A. If A can be transformed into C and C can be transformed into B, then A can be transformed into B. And from these two, we get that if A can be transformed into C and B can be transformed into C, then A can be transformed into B, and we will use this later on. The actions of cutting and rearranging do not affect the area of the initial polygon. So, in order for A to be able to be transformed into B, it is absolutely necessary that the area of A is equal to the area of B. We will prove, therefore, that given two polygons A and B of equal areas, there is a way to cut A into smaller polygons that rearrange from B. So, here are the steps that we will present. First one is that polygon A can be cut into triangles for any given polygon. The second one, any given triangle can be cut into smaller polygons that rearranged can form a rectangle of equal area. Third one, any given rectangle can be cut into smaller polygons which rearrange from a rectangle with one side of length 1 and of equal area. And four, all these rectangles with one side of length 1 can be put together to form a bigger rectangle C with one side of length 1 and of the same area as A. According to all these steps, we can say that A can be transformed into C for any polygon A. B is also a polygon, so B can be also cut into smaller polygons that rearranged from rectangle C prime, a rectangle with one side of length 1 and the same area as B. Because A and B have the same area, it means that C and C prime are actually the same rectangle. So we will use the thing that we proved before. If A can be transformed into C, B can be transformed into C, and we get that A can be transformed into B.
So the step 1 of our solution consists of the triangulation of a polygon. So for a convex polygon, it can be cut into triangles by choosing a vertex and tracing all of the diagonals which start from that vertex. For a concave polygon, it can be cut into convex polygons, for which we repeat the previous steps mentioned. So step 2 of our solution consists of transforming any given triangle into a rectangle. So the first step is transforming triangle ABC into rectangle BCYZ. For that, we use the following notations. X and Y are midpoints of line segments AB, respectively AC, and D is the line parallel to AC that goes through B, and Z is the point of intersection of D and XY. And the figure that we added in this slide basically represents how we can make a parallelogram out of the triangle. And the next step, in order to form a rectangle from that parallelogram, so we will transform the parallelogram ZYCB into a rectangle ZZ prime YY prime, in which Z prime is the foot of the perpendicular from Z to BC, and Y prime is the foot of the perpendicular from Y to BC.
Step 3, we will prove that any rectangle can be transformed into a square with the same area, which also means that any square can be transformed into any rectangle of the same area. From these two observations, it concludes that any rectangle can be transformed into any other rectangle of the same area. So any rectangle can be transformed into a rectangle of the same area and with one side of length 1. We will consider the rectangle A prime, B prime, C prime, D prime. with side lengths A prime and B prime. A prime smaller than B prime, and the square of equal area x, y, z, t, with side length of C equal to the geometric mean of A prime and B prime. We will transform the rectangle A prime, B prime, C prime, D prime into the rectangle A, B, C, D with sides of lengths A and B with the following properties. A is smaller than B, and B over C in a specific range of values. We need that property in order for the proof to look as simple as it does. If the ratio is not in that range of values, it will either not work with this method or be a lot more complicated. But we can use some simple transformations to modify B while C remains constant. And ABCD is that rectangle with side lengths A and B that respects all these properties. And we split both the square and the rectangles into different polygons. And we show that we split them into different polygons that can be shown to be congruent. For example, on this image, the polygon EFIKJ is the same as GNOZF. And for every polygon that we cut ABCD into, it has a correspondent in the polygons of X, Y, Z, T. So to summarize and to show the full method for transforming any polygon A into any polygon B, we first cut A into triangles, then we transform each of those triangles first into a parallelogram and then into a rectangle. We transform each of those rectangles into a square of equal area, which we then transform into a rectangle with the same area and a side of length 1. Then we put all those rectangles together to form a rectangle of with area equal to A and with a side of length 1. We repeat steps 1, 2, and 3 for polygon B, and then we do them in reverse order on polygon C. And thus we have transformed polygon A into polygon B. And here we have some specific cases. For example, here we have a square and a triangle, a square and an equilateral triangle of equal area. And this is the minimum number of pieces in which we need to cut one polygon in order to transform it to the other. And we have a few examples. This one is particularly interesting because of the rotational symmetry that it has, which isn't that often in this situation. You can see this one is very complicated. This one also has a nice symmetry down the vertical line.
So now we can present our conclusions. So we proved that any polygon can be cut into triangles, and any triangle can be dissected into polygons which rearranged form a rectangle. Any rectangle can then be transformed into a square of equal area, and any square can be transformed into any rectangle of equal area. In other words, any rectangle can be dissected into smaller polygons, which after a series of rearrangements form another rectangle of equal area. Therefore, any polygon can be transformed into another polygon of equal area. In conclusion, this is the procedure, not necessarily the most efficient, to dissect a polygon A into smaller polygons, which rearranged form polygon B. And thank you for your attention. If you have any questions, please
Thank you for the presentation. It was really clear. I'm just having a look if there is some question in the chat. I've got a question in the privilege here.
Hello, can you hear me?
We're going to have a question from here.
Hi, can you hear me?
Do you hear us? Yeah, can you Okay. Which way is the question?
So that's right. We spoke about the optimality of the transformation and said that. Okay, it's really bad. I did a chat.
You try, yeah. So the question is
No, we haven't tried to estimate the minimum number of steps needed, but it differs from situation to situation.
Okay, thank you for the answer. As we are really late, we're going to do the break now, and we start again with the group of students. Thank you very much. Okay, the break is over. We're going to have now a presentation from Cluj in Romania, and it's called the modélisation de croissance d'un arbre. Mark, you're now allowed to share your presentation.
A second, please. All right. Let me just. Is it okay?
Yes, it's okay. Can you speak a little bit louder? Then we can
Yes,
hear you
yes,
properly.
yes, of course.
Thank you.
Great. So please start. Potfi, Andrei. Already?
Yeah, so we had research topic 3. So each branch evolves into 2 different parts. We'll consider the sign plus to indicate a development to the right and minus to the left. For example, B plus means the left part is of type A and the right part is of type B. We consider the vertical section of a tree that we model after 3 types of diameters. A trunk A can evolve into A 45%, B plus 20%, AB minus 20%, B minus 15%. A branch B can evolve into B 45%, a branch C can evolve into C 45%. It stops 55%. We start from trunk A, simulate and study the evolutions of the tree, give the results above the height of the tree, about the number of branches, and the life of the tree.
All right. So firstly, we created a C++ program. I'm going to present it. It calculates the probabilities of each branch after a number of years. So we have a bidimensional table called DP from dynamic programming, and an integer n, which represents the number of years after which we want to know the probabilities. And we are using a binary tree. That is a tree where each node has exactly 2 children nodes. And the depth of a binary tree is 2 to the power of n minus 1, considering we start from level 0. At the level 0, there is the first node with the probability 100%. For each new level, we calculate the probabilities for each type of branch based off some simple math formulas and the parent node. And the results are outputted in an external file, so they can be visualized much better and easier. And right here we've got a C++ program. It's quite short. It has 60 rows only. And right now we input 5 and A. That means that we want to find the probabilities after 5 years, considering the starting branch being A. And in the external file, we can see all the branches with all their probabilities. shown really nice. And for example, the last branch has a 97.25 probability of being empty after only 5 years.
Okay, now my colleague said that there is a binary tree, and now we found a property of binary trees that if you number the nodes from the last level from 0 to the 2 to the power of n minus 1, and we take a random node, let's say 6, and if we transform it in the base 2, we can find the road from the first level to this node. So 6 in the base 2 formula of 6 is 110. So 1 means that we go to the right, and 0 means that we go to the left. So how can we reach the 6th node? Is taking right, and left. Using this, we found the formula of a node to be A, B, and C. So a node, the probability for a node to be A is 65 over 100 to the power of how many zeros are there in the base 2 form times 20 over 100 at the power of number of ones in the base 2 form. This is because 65 over 100 is the formula is the probability to go to the right to another node that is A, and 20 over 100 is the probability to go to the left, to go in another node that is A. So, for example, if we take 6, the probability will be only 2.6%. Using these formulas, we found another two for node to be B and for node to be C. So it's the sum of 65 over 100 to the power of number of zeros times 20 over 100 to the power of numbers of 1 divided by when we go from node that is A to the node that is B over times 35 over 100, that is the probability to go from a node A to a node B. And the formula for C is the same, but we go to another change. So we have a change when we go from A to B, and another change when we go from B to C. So we do this 2 times. So we divide to an X, where's the place when we change from A to B, and we divide it another time to Y, where's when we change from B to C. And we multiply it by 35 over 100 squared. That's the probability to change. So basically, we divide it with X because we don't want to go another time to another node that is A. Okay.
We also use some Markov chains, chain theory, to approach the problem a bit more technically, more mathematically. And, first of all, to prepare the matrix which we need to then power by n to find out the probabilities that we want. For our Markov chains, we have to find out the probability of a node to be of a certain type, starting from a branch of a certain type. So now you'll probably see that we have a lot of probabilities which have commas in them, so like 42.5% or 77.5%. Well, as we said, we had a convention that every time we have a development, we're going to develop into two different nodes. So using Markov chains, we're going to find out the probability of a node to be of a certain type after n developments. But that node is going to be random. So when we develop from a branch of type A, we're going to have two different nodes. So we're going to have to divide that certain probability by 2 because we don't know if we're in the left part or the right part of the development. For example, from a trunk A, we have a 45% probability of it still being a 20% for AB plus and 20% for AB minus. So if we sum up 22.5% plus another 20%, we're going to have the 42.5% we described there for nodes to be of type A if we're starting from a branch of type A. So we also found out the probabilities for the others. So the probability of a node to be of type B starting from a branch of type A is going to be 35% and so on and so forth. And we're going to use Markov chains theory to determine of what type a certain node is after n developments. And to start, we have to put all those probabilities into the matrix X. And to find out the probabilities after n developments, we're going to have to calculate x powered by n, which will give us all the information on the first line of this particular matrix. The first element on the first line is going to tell us what the probability is of our branch to be of type A after n developments, the second element to be of type B, then of type C, and the last element on the first line is going to tell us what the probability is of the branch not to exist. So now the mathematical problem here is to calculate x powered by n, and to do this we decided to use the Jordan canonical form. We can write x as P times a matrix A, which is made up of x's eigenvalues on the diagonal and another 1 on the second line, third column, because the matrix X is not diagonalizable, and times another P powered by a -1, where P is obviously invertible. Now, the advantage with this form is that if we calculate x powered by n, if instead of simply using x, if we use P times A times P powered by -1, and we can see we're going to end up having P times A powered by n times P powered by -1. So our task is to simply calculate A powered by n, which is much easier to do.
So considering it is quite a tedious job to manually calculate such a matrix, we decided to use Wolfram Alpha, which gave us the following results. We found P and P powered -1 with Wolfram Alpha, and this Wolfram Alpha is an aligned computational knowledge engine.
So to determine the maximum lifespan of a tree, I built a simplified Markov chain in order to maximize the length of the growth for the tree. So for an A-type branch, if we go to AB minus or AB plus, for example, for the Markov chain, we consider only the growth of A-type branches, because we are interested only if we reach the finish of growth for every single type of branch. As well, for a B-type branch, we can go to B minus or B plus. But in the Markov chain, we only go to B for the same reasons, and so on. Based on this Markov chain, I determined the following matrix that, after being raised to the nth power with some help from a online calculator, can help me determine the probability for the the end of the growth process after n trials, represented by the fourth element from the first row from the matrix m raised to the nth power. And now with all this information from the matrices, I can pretty much calculate an expected value for the number of trials that run till the end of the growth process. We represent the number of trials with an random value y, that's an integer number, being an integer number greater or equal to 1. So its medium value is calculated using a weighted average, pretty much. And with the weight for each random value y being the probability p of y that is determined from the matrix M, being again the fourth element from the first row from the matrix M raised to the yth power. Based on this, we pretty much came up with the following formula shown on the slide that accurately determines the lifespan of the tree.
Thank you very much for your attention. Thank you. Questions?
We're going to tell you right now. There is no question in the YouTube chat, but there is one here.
Can you hear me?
Can you hear the questions?
Yes.
So on last slide there was this word, this eigenvalue. Can you explain a bit what that is?
Can you speak a little bit louder, please?
Just ask you, what does mean eigenvalue in the, I think was like in the one of the last slides.
So eigenvalue, well, every matrix has a characteristic polynomial. That's what we call it. Maybe you heard of the Cayley-Hamilton theorem, which tells us that every matrix, if we put it in that respective polynomial, we're going to obtain a norm matrix. And those eigenvalues, we calculate them by calculating determinant of A minus a random lambda times I4. And if you try to calculate this determinant, you're going to end up with a diagonal determinant, and that's how we ended up finding out that they're 22.5, 42.5, twice, and 100. And these eigenvalues give certain information about the nature of the matrix. So, for example, the sum of the eigenvalues is the sum of the elements the matrix has on its diagonal. If you simply multiply the eigenvalues, you're going to end up with the determinant.
Thank you. Other questions? I've got one. On the first slide, there is like some really nice draws of trees. Did you generate these images yourself, or is it images that you found out?
No, I found those.
Okay. Thank you very much. I don't see any. I'll just check if there is other questions. Yeah, I've got another one.
Why did you choose to program it in C++? So why this choice of language? You already know C++, or what are the reasons behind it?
Did you hear the question?
Sorry, can you speak a bit louder?
Yeah, I'm sorry. I'll translate. The question was, what did you use C++ language? Is there a technical reason, or is it because you know it, or?
Well, C++ is more familiar to us, to Romanians, because we do it in school, and it's a bit faster than Python, and it's more convenient because we can generate a lot more nodes, and
You're
can have
talking
more
about.
data. I'm sorry, what?
No, you're talking about that you're learning C++ at school in Romania, but you're in 12th grade, I guess, and are you studying as well all this matrix theory and eigenvalue and determinant at school, or did you discover with this MATH.en.JEANS project?
We study matrices at school, but eigenvalues are out of the school curriculum, but we learn them preparing ourselves for certain mathematical contests and activities and whatnot.
Okay, thank you very much. We're gonna, if there is no more questions, we're gonna start with the next presentation. So now we have a group of Padova, and I give you the hand with your presentation.
Okay. Perfect. So we are the group of the Aviator, and this year we have solved the problem of the Aviator. The problem we faced posed the following situation. An Aviator crashes in a desert region. Fortunately, he survives, and it turns out that he was carrying 1,000 cans, each containing a ration that allows him to travel 1 kilometer. He can only carry 100 cans in the backpack. The question were, can he hope to reach a village 200 kilometers away? How far can he go without any external help? So, to answer, it was decided to build a model based on two assumptions. The Aviator carry all the cans at his disposal, going back to take the leftover cans. Before depositing the cans to go back for them, he travels a distance of 1 kilometer. In this way, a piecewise defined function was built that is able to describe the kilometers traveled in relation to the cans used. In particular, starting from an initial capital of 1,000 cans, he begins to advance up to a distance of 1 kilometer from the initial position, when 98 cans are deposited, before going back to recover the other 900. The aviator's motion is periodical, in particular, if initially for each kilometers traveled, the aviator loses 19 cans, when instead the cans to be transported decrease, those consumed per kilometer will follow the same trend. The factor key equal to the distance at which the aviator arrived before the change, so that the function is continuous in the interval 0 point plus infinite. Using a 1 kilometer step, the final distance would have been 212 kilometers from the starting point. This allowed us to answer the first question. Indeed, the function and the related graph clearly indicate that the aviator, through this model, is able to reach a distance that exceeds that required by 12 kilometers. So now I leave the floor to my friend Alessandro Doria.
Good afternoon to everyone. I will explain to you the second part of the problem. And so this is the part in which we tried to answer to the question, how far can the aviator go without any external help? This part has been approached with the purpose of deducing a general rule. So it has been decided to build other models that were based on the same assumption of the 1 kilometer model, but varying the length of the step x. So 3 models were built that are with steps of 0.1 kilometer, 2 kilometers, and 10 kilometers. So this is the model with a step of 0.1 kilometer. And as you can see, both the graph and the algorithm is very similar to the model with of 1 kilometer model. And the final arrival point is 212 kilometers. Then we have the model with a step of 2 kilometers. And also this one is very similar to the model with 1 kilometer, with a step of 1 kilometer. But in this case, the arrival point is different. It arrives at 210 kilometers. And when the aviator has 502 cans, he leaves 2 cans instead of taking them with him, because it is more convenient. Then we have the last model, that is the model with a step of 10 kilometers. In this case, the arrival point, the final arrival point is different. It is 200 kilometers. And in this case, it is similar to the model of with a step of 2 kilometers, because in 4 situations, it is convenient to leave down 10 cans in this case, so a number of cans that corresponds to the length of the step. So in the models with a step greater than 1 kilometer, it is convenient for the aviator to leave a certain number of cans that corresponds to the length of the step x. Then, after further analysis of the shown cases, a certain regularity was recognized in the algorithm. So, placing conditions of existence to the step x, it was possible to determine a series of equations that gives the number of remaining cans. And then I will leave the floor to my colleague, Picchioni. Thank you.
Okay, so we identified the necessity of recognizing a new variable, which we identified in n, and which describes the number of steps that the aviator has made. With the number of steps, we mean that the number of times that the aviator has moved all the cans that remain to the next step. And so we noticed also the fact that n multiplied by x is the distance that the aviator traveled. So we, from this notice, we developed an equation which describes the passages that we used to do manually. And this is the equation, and the contracted form is the following. And we also noted that this equation is only valid for the first step. So for the first time that the aviator moves all the cans to the first step. So we noticed the necessity of analyze in a deeper way the variable n, and we tried to do it seeing a correlation that we noticed from the different models, and we've seen that the correlation is between the change of the figure of the 100 and the distance traveled. Of course, because if the figure of the 100 changes, the number of passages that are needed to move all the cans to the next step is lower. So we have seen that the n that we considered in the first slide is the result of the ni, which we consider n with 1 and with 2 and n with 3, with all the n to the 10. So we consider that ni is 6 divided by x, considering the number of integer number following. So the equation that we found before changed and has become the following equation. And so we tried to write an algorithm that could do the passages that we used to do manually. So the algorithm, given an x and an n, calculates the multiplication between the two variables, finds the interval in which has been calculated the number of the remaining cans based on the length of the step, and calculates the totality of the remaining cans by adding them up. And this is an example of the model of 1. So to the right, you can see the equation that we write in the first slides. And to the left, you can see the passages of the algorithm and the result of 212 kilometers made by the aviator. So I leave the floor to Michele, which will conclude.
So with the Python program, we then made the program calculate the distance reached using steps from 0 to 50. Although the problem needs to be fixed because it is not yet able to understand when it is convenient to leave some cans on the road. In general, it shows a downward trend. So as the pace increases, the final distance will gradually decrease. This allowed us to come to conclusion of the problem, answering that the model that follows the aviator with step of 1 kilometer, which is the same as the decimals of 1, is the most efficient. Thank you all for the attention, and I'm here for your questions.
No question in the chat at the moment. Any question here? Yes.
How did you define the functions modeling the path made by the pilot for the very first time? Did you do a Python program, or did you just try and find out?
In the first case, the equation were calculated mechanically, while in the last function and in the last algorithm, we have used Python, and we have understood that they were the same equations as the previous model.
Thank you. Any other questions? Yeah.
So you said that the program is not perfect yet, that you need to make changes. Have you ideas how to change the program to include these more intelligent versions?
Yes, the program has to be fixed, but we don't know well the way of fixing it, because it is really complex to find a way that is valid for all the numbers and all the lengths of the step.
Thank you. A last question, maybe? No. So thank you very much.
Perfect.
We now have a group from Cluj, and it's going to talk about percolation. Amalia, you can share the presentation, and if I need to change, just tell me.
Hello, I am going to share the presentation.
So you're now allowed to do it.
Thank you. All right, can you see my screen?
Yes.
Yeah, but you have to, yeah, perfect.
All right. Good afternoon, everybody. I am Dojka Rares from Cluj-Napoca, from National College Emil Rakovica.
I'm Maria Hatzegab, and I'm also from National College of Emil Rakovica, Cluj.
Our main researcher was George Tsurkash, and he works here in Cluj-Napoca at the University Babeș-Bolyai.
Problem statement: the soil is modeled by a grid of 100 per 50 cells with a certain density of occupied cells represented by color black. The water blue is on the top lower, and it will fill every adjacent cell that is empty, coded with the color white. Let T be the number of iterations required by the water to cross the entire ground from top to bottom. Establish the relation between the time t and the function d based on the simulations. Either a cell is black with a probability d of intensity, or the soil grid has a density d. The two cases are different to program and compute.
Right. To understand better what are we dealing with, here is a Python animation that explains our problem. Well, we'll just wait until the animation is over, and in the end, you will see with green is colored the shortest path for the top layer cell, this one with green, to reach the bottom layer. So it is colored in green.
Results: an iOS app, a Python program, and some graphs.
Oh, well, the Python program was in the previous slide, this one. Firstly, let's start with an useful app. We have developed an iOS app using the programming language Swift and the user interface creator Swift UI. In this mobile app, you can see how the Lee's algorithm and the multi-agent theory work. Moreover, you can experience the visualizing of the problem by watching how the water percolates the ground in the two cases mentioned in the problem statement. Here is an implementation for the Lee's algorithm, which is included in a button action in the app code. When the button is tapped on the phone screen, the algorithm runs just one time for only one cell. And after that tap, the final result is updated. Now I'm going to present you exactly what an app includes. When you open the app, well, there will be a menu screen from where you can navigate the 3 games. The first game shows you exactly how the Lie algorithm works with just one cell. There you have a starting cell, this one in this case, with the lighter blue, and a finish cell colored in red. At the end of the process, the app will show you in how many moves could the water, for example, percolate to this finish point. And in this particular situation, the destination is reached in 9 moves. Well, we can verify this value by counting 1, 2, 3, 4, 5, 6, 7, 8, and 9. So it's the right answer. The second game is about the multi-agent theory and how does this principle works. In this view, you can experience a race between the color blue and the color orange. And both colors are percolating through the matrix at the same time. In the end, the app will show you which color wins. In this case, blue wins, because you can see here that this blue cell has is adjacent to this red cell, which is the finish one, and there aren't any orange cells that are adjacent to the red one. The third game, and the most important of all of them, is about the problem statement. Because the screen of the phone is too small for a 50 by 100 matrix, I decided to make a smaller one, 10 by 20 matrix. Using the multi-agent algorithm and theory, all the top layer cells percolate at the same time. In the matrix, at the end of the process, there will be a message on the screen which shows you in how many moves the whole water could percolate through the ground. So on the last row of the matrix, we will have the values of how many steps were needed to get there. Our result, this 13 in this case, will be the maximum value of these. So after each Lie algorithm runs for each cell, we will know which is the maximum value from the last row. And this is the answer of the time in which the whole water percolates through the ground.
The second approach, graph. So first of all, this approach is based on Lie's algorithm. It consists of 4 steps: initialization, we mark the starting point. Secondly, a wave explanation, mark the unlabeled neighbor accordingly to the previous generation. So the value of a neighbor is the value of previous generation plus 1. Break trace, from the target point, check the neighbor with the law or value and add it to the path. And the fourth one, clearance, delete all marks so that the optimal path remains for future use. We will consider a percolation complete if and only if all the bottom points are percolated. So the empirical data suggested an interesting correlation between the median time of complete percolation and the percentage of unpercolable cells. So 0% trivial case, minimum time for percolation, between 0 and 35% approximation with function, and more than 35% percolation only in exceptional cases. Important deductions arise from these results if the percentage of unpercolable cells tends to 0%, the complete percolation time tends to be equal to depth of terrain, in this case 50. In the percentage of unpercolable cells is over than 35%, percolation appears only in exceptional cases. And if the percentage is of unpercolable cells is between 0 and 35%, we try to approximate a function that marks our empirical data. So the description of the function is that we got the function defined on a closed interval of 0 to 35. This function is continuous, and the x represents the percentage of unpercolable cells, and the function tends to get the medium time of complete percolation. As a result of the continuity, we can now approximate any value of this function, where x is between 0 and 35. So we got this approximation due to analysis of tests. Moreover, we got this approximation due to analysis of the values generated from 1,000 tests we run from a wide range of densities. What's next? Considering all the above, our research will not finish soon. We are focused to improve our research by getting better approximations using the Lagrange and the novel polynomial interpolations. Additionally, we want to develop our research by using cells with different densities, and moreover, we will follow different trends of percolation, given the fact that percolation is a very complex process. Finally, our goal is to expand our research using different grid sizes.
All right, and thank you very much. And as I recall that we have 17 minutes to present our presentation. I have the app more than just photos on my PC, so I can show it to you. And how does it work? So this is an iOS app, an iOS iPhone 13 simulation. So this is the main screen, and here is the single agent view. And you have to tap this button, next phase, and when the red cell is reached, then a message is received by the user, and the destination is reached in 13 moves. Here is the second one, the second view, and as you can see, blue is trapped in here, so it's pretty obviously that this time blue loses the battle and the orange color wins. The whole grid will be filled by the color orange, and on the screen will show that orange wins. This is the two cases that I talked about, and the density here is a random number between 0 and 50% of density. Finally, all the water drains in 17 moves. And in the second case, well, you can choose what density do you want. Well, let's say 35%. And the cells, well, it's like the ground has, like in physics, the ground has density 35%. So now the water can percolate through the ground. So every cell of the matrix will be filled with water. And the result will be smaller in this case, 12. Thank you very much for your attention.
Is there any question in the public? Yes.
Yeah, I have a question. How long do you do
I'm sorry, I didn't quite hear it.
The first one was how long does it take you to program and to finish your application?
Well, it took quite a lot because as you could see, well, there were 3 pages, and the third one with the percolation game had 2 included, 2 views included, and I think that the whole application, well, the app I started in September, and I finished it in February, so quite a lot of work.
Yeah, well done. Is there any other question? Yes.
Yeah, so thank you very much for the presentation. I was surprised to see that you used MATH because it's not a very well-known open source program. So how did you think about using it?
Can you repeat it, please?
What's the name?
Manim.
Manim. Apparently, you use Manim as an open source application, and it's apparently not really known. I didn't. And how did you get the idea to use it?
Well, my group thought about how to do a graphic in Python because that graph was just a photo, and the Manim open source library provides you an animation. We wanted to put it to make it more beautiful, or and we thought that Manim was a good idea.
So too. Very nice idea.
Thank you.
Thank you very much. We try to get a few minutes, not to be too early. So we thank you again.
Thank you.
And we now have a presentation from Padova, which is called the skyscraper game. Padova, you can now share your screen.
Good afternoon. Today, me and my colleagues will present a problem entitled The Skyscrapers Game, which consists of a city represented by a 4x4 grid, which can be filled with 10, 20, 30, or 40-story high skyscrapers, which can be indicated respectively with the numbers 1, 2, 3, and 4. On each row and column, there can be only one skyscraper of a given height. And on the edges of the grid, each number describes how many skyscrapers can be seen from that certain point of view. And consequently, the taller skyscrapers cover the lower ones. So given a 4x4 grid, we had to answer the following questions, which were firstly, to find an example in which the skyscrapers are not disposed uniquely, and also to find one in which a city does not exist. Then the other question was to find a rule according to which the game can be solved uniquely, and then to possibly find a rule, a universal one, to solve the game. So to further understand the possible disposition of the numbers in the grid, we analyzed its possible symmetries and rotations. So we started from the base position and we observed that there are 7 total possible symmetries and rotations. So we arrived to the conclusion that rotated or symmetrical edges do not change the inner part of the city. So it's the same city, but just rotated or symmetrical. So bearing this in mind, static cities becomes easier, but also quicker. And here it can be observed an example of horizontal symmetry, where the two cities are symmetrical on their vertical axis. And the first thing we did was to study smaller grids in order to simplify the problem. We firstly observed the 1x1 city, but it had only one solution, so we went on to the 2x2 one. But there are 2 equivalent solutions that are symmetrical to each other, so this step was not that functional after all, since each of these cities has only one solution. So we decided to focus on the 3x3 grid. First of all, we decided to look at the individual lines by looking at the numbers on the extreme points. So we understood that not all the possible combinations create a valid row. So we observed that the valid combinations of extremes are only 3, and they are the following. So 1 and 2, 2 and 2, and 1 and 3. So in the end, we observed that all the 3x3 cities are combinations of the 3 rows described in the picture, under which there is a graph of the possible extremes in a row of the 3x3 city. So in the 3x3 case, we noticed that given a valid border, the city can always be unique for 2 main reasons. The first one is that the possible row combinations are only 3, and there are only 3 rows and columns to fill. And then the last reason is that there are only 3 ways to order the rows in a valid way. So we have just 3 unique cities.
So then we went back to the 4x4 grid, and we observed that there could be only certain combination of extreme, like in the 3x3 one. And this combination are 1, 2, 1, 3, 1, 4, 2, 2, and 2 and 3. And obviously this combination can be inverted thanks to the symmetries that my colleagues explained earlier. So then we calculated all of the possible combination in a row by doing 4 factorial, which is 24, because a row can be, because in a row there could be only 4 unique numbers, so this is why we use the factorial. And in this slide, we can see all of the combination of a row, of the rows that we developed. After analyzing a row, we started developing an algorithm to solve a city. And we started by looking at the analysis of the row that we just did. And we noticed that certain extremes have a particular way that the row must be filled. For example, with the 1 and 4 as an extreme, there must be 4, 3, 2, and 1. With 2 and 3, 3A, and 4. With 3 and 1, A, B, C, and 4, and so on. Where A, B, C, D, and E are sets that represent the value that a certain skyscraper can have. So for example, in the case where the extreme are 2 and 1, A must be 1 or 2. Now my colleagues will explain the rest of the algorithm that we developed.
Can you share your presentation again?
Excuse me?
Can you share your presentation again? Because at the end, your slide didn't change.
The wrong thing, sorry.
Thank you.
Wait a second. Here. Can you see it?
Perfect.
Okay, thank you. So I'm going to go over the main point. So we have because we have the presentation now. So yes, we have the introduction to the problem, which is a 4x4 grid. And on the rows and columns, we have unique numbers. And taller skyscrapers cover the lower ones. Then we study the symmetries and rotations of the cities. So we could study cities quicker. And we studied then smaller grids. So 1 by 1, 2 by 2. We went also to the 3 by 3, thanks to which we understood that not all the possible combinations of extremes create valid rows. And we also then studied the row's extreme points. So we studied the single row, and we realized that a city is not valid if it has invalid extreme combinations. Then we studied then all the numerical combinations in a row, which can be 4 factorial in the 4x4 case, so 24. And we also generalized the row, the single rows, with the generalization scheme that is fundamental for solving the city. So the rest of the algorithm to solve a city given the extreme points is the following. So first of all, we solved all the 1, 4 rows and columns. So the rows and columns that have 1 and 4 at the extremes. By putting 4, 3, 2, 1 in a specific order, in the internal 4 corresponding to the external 1, and then putting them in descending order. And we also solved all the 2, 1 rows and columns by leaving blank spaces where the numbers were unknown, so where the numbers were variable. Then we do this with the same step for 3, 1 rows and columns and 3, 2 rows and columns. But many blank cells are still unsolved in the grid. We will take care of these in the next stages. So we had to work on the unknown cells which can have variable values. For example, a cell belonging to the set A can be either equal to 1 or 2. So to solve this, we looked at the inner rows first, and using the generalization table shown in the previous slides, we filled each cell with the corresponding value. In the first row, for example, we have A, D, 4, and C, where the numbers we put are written in green. And we did this for every row. And then we looked at the inner columns, and we did the same process. So for each cell, we obtain an intersection between 2 sets. So for example, if a cell belongs to A intersecting B, then that cell will have the value 1. So the city has not been solved yet, because some cells take values belonging to the intersections of the 5 main sets. And we noticed that any intersection between these sets is actually equal to one of the 5 main sets, or a number between 1 and 3. No intersection yields the number 4. So we developed a table which reports all the possible intersections between the 5 sets. And we can see it on the right. And this table is fundamental to solve the city. Because after solving the intersection that we obtained from the previous step, we obtain new constant values and cells with new sets. And as it can be seen, lots of rows / columns contain 3 unique constant values, which are depicted in a light orange. For each of these, we assign to the unknown cells of the row the remaining value of the 4 possible. So for example, if we have 4 to x3 in a row where x is an unknown value, x must have the value 1. And this is a fundamental concept, because if this step is applied recursively, we can obtain a solution. But the described algorithm can only solve unique cities. For example, in the first example, we have a non-unique city, which was solved using the first algorithm. So to solve this one, we have to use another algorithm. So for every unknown value, we subtract the corresponding set to the set of known values in the row/column in which the cell is contained. So we can see at the corners we have C values, and these values cannot take values 1 or 4. So they must be D sets. And now for the first cell that we encounter, we give it the first value that it can take. So in the case of the first upper right cell, which was a D cell, we give it the value 2. And then we find all the calculable rows using the method explained before of the 3 constant values per row. And then we apply these steps recursively for each value that initial cells can have. But in case there were still unsolved cells in these solutions, we apply the previous steps recursively for each solution obtained, thus having all combinations of solutions which can be 2, 4, sometimes 3 or 6. This part of the algorithm was not formalized because we didn't have time to build an algorithm to actually solve a unique city. But for unique cities, we actually built an algorithm to solve them using Python. And finally, as the last step of our journey, we developed an algorithm to find all unique cities to determine which criteria make a city valid. Using a Python program, another one, we calculated all the possible combinations of columns using the 9 possible combinations of extremes that we saw earlier. So the 5 that we explained, plus all the inversions. Of course, the 2 extreme points, if inverted, are still 2. And then we checked which cities that we obtained were valid and unique. So we obtained a total of 7 valid unique cities, or 56 if we count all the symmetries. Therefore, if a city is a symmetry or a rotation of one of these cities, then it is always valid and unique. Non-unique cities, though, are not taken into account because a city might be actually non-unique and valid, but according to this statement, it might seem invalid. But we just consider unique cities in this case. And here are all the 7 valid unique cities without their symmetries. We didn't write the inner part of the city because it's not fundamental to recognize a city. We just needed the borders, which are the following. And we think that it's pretty interesting that, at least from the point of view of unique cities, such a vast and complex problem boils down to 7 possibilities. If we count maybe the non-unique cities, we might get more possibilities, more combinations. But for now, this is the end of our presentation, and we want to thank you for your attention.
Thank you very much. We're gonna have a few questions, but just before, if Yash hear me, I'll ask you to present in the other room with the link. Did you get the message?
Okay.
It's for Yash, it's not for you.
Okay.
Oh yeah, okay, they leave. Thank you very much. So I check if there are some questions. No question in the chat. Here in the publicum, are there any questions? We don't have question right now.
Okay.
I've got a technical one. Is the next group presenting? I'm sorry. Is the next group from Padova presenting Crazy Ball is available now?
Yes, they are available.
Can be? Okay, because we have a timetable changing, and
no problem.
if it's okay for you, then we would like you to present Crazy Ball now.
No problem at all.
Thank you very much, and thank you for a presentation.
Thank you.
Padova, you can plug your presentation, and you can start whenever you want.
Good afternoon. Can you hear me?
Yes, we do. It's perfect. We hear you and we see you.
Perfect. Today we're going to talk about the crazy ball problem. We're the Romano Bruni Scientific High School. And starting from the problem, today a ball fell down the stairs. It bounced on the first step twice, then on the second, on the fourth, on the fifth. The problem asks us this question. If an initial velocity is given, on which step will it bounce? Can I build a stair made of steps with the same length and height in order to make the ball bounce once on each single step? Can I build a stair made of different steps? I will pick them. Let's start with an example. Here we have the initial velocity on the vertical component being 1 meter per second, while the vertical component is 0. The height is 0.5 meters, is equal to the length of the step. And then we approximate the acceleration of gravity to 10 meters per square second. Using the dynamic formulas, we reached some results, which are that the ball bounces on the first step with a range of square root of 10 meters divided by 10, and a final velocity on the vertical component of square root of 10 meters per second. Next, it will bounce on the third, on the fifth, and the ninth step. I will leave the floor to Michele.
Okay, thank you. We started from an extendable stair, so the ball is considered as a material point. Okay, and the energy is always the same. We studied the ball speed for each bounce and how it changes. We use dynamic, so we know that the final energy is equal to the initial energy. And if we isolate the final speed, we find that it is equal to the square root of the square of the previous speed minus 2g delta h. So now we can find the speed from the previous speed, and in general, the function of the speed is the square root of the v0 square minus 2g delta h n, because, for example, v1 is the square root of v0 square plus 20, and v2 is the square root of v1 square plus 20, that is equal to the square root of v0 square plus 20 plus 20. Okay. Then we used also the cinematics.
So we use the formula of the parabolic motion, and we found the vertical component of the final speed. And it is obviously it is negative, but this isn't important because after the bounce it becomes positive. Okay, so this is the function. We use the v0 is equal to the square root of 11 because it was the result that we found in the example. From the speed function, we found the function also of the range. So we took the formula from the parabolic motion, and we substituted the function of the speed, the vertical speed, but with n-1, because to find the range at the nth step, we need the speed of the step n-1. Okay, and now I leave the floor to Matteo.
Okay, let's do some consideration about the angle by which the ball arrives at the step. So the tangent of the angle can be calculated dividing the epsilon component of the speed by the x component. So we substitute the function which describes the epsilon component of the speed on the formula, and then we get that the angle at the n step is equal to the inverse tangent of epsilon component of speed divided by x component. So let's do some consideration. We notice that the limit for n that approaches plus infinite of the velocity at the n step is plus infinite because we work only with the classical physics, and the limit of the angle, the limit for n that approaches plus infinite of the angle is 90 degrees, and also the limit for n that approaches plus infinite of the point of range is plus infinite. So due to conservative forces, it is impossible to build a stair with an infinite number of equal steps, where the ball can bounce just one on each step. In fact, the range keeps increasing. So now I leave the floor for Matteo.
Right, so we tackled the problem one more time, but this time we fixed the length of the steps to be equal to each side, so 1 meter. All the other considerations were left equal to the previous problem, and the issue we encountered was with calculating the range of each in each step. This is because we didn't know how many steps with each jump the ball would have traveled. So we used this formula that allowed us to find the parabola for each jump, and we could intersect it with the bisector of the second and fourth quadrant, and this allowed us to know in which step the ball would fall. And from this we can find a recursive function that tells us on which step the ball will fall. Now I will leave the stage to Francesca.
Okay, so lastly, we want to talk about the non-ideal system. So where the ball is still considered as a material point and where the length and the height of the stir are fixed. But in this case, the mechanical energy is not conserved. So as a consequence, obviously, the ball loses a sort of amount of energy that we actually wanted to figure out how much it was. So we started by the initial energy, which was multiplied by a sort of energy, which was obviously unknown, and we compare it with the final energy. And then we isolated the energy, which is our unknown data. And so we started by working with the unknown percentage and the range as well, which previously it was talked about. And from the range in particular, we isolated the initial velocity. And we can see a lot of calculus in this slide, but at the end, we also set some conditions concerning the velocity and the range itself, as well as the height. In conclusion, with a range of 1 meter and a velocity of 1 meter per second, we figure out that it is impossible to work in a system like that because the percentage was negative. So we decided to set new condition in order to make the non-ideal system works, and with a range of 2 meters and a velocity of 1 meter per second, we figure out that the percentage of energy loss for each bounce is approximately 0.78. So that's it. Thanks for the attention. And if you have some further questions.
We lost your presentation. Is it over or?
Yes, if you have some question to ask.
Okay. Thank you. Is there any question here? I'm checking on the YouTube. I don't have any question on YouTube. Maybe no. Yes.
Why did you choose a physics subject for your presentation?
Did you hear the question?
No, we can't hear you well. If you
Okay.
can
The question was, why did you choose a physics subject for your presentation?
Okay, so we were interested by the problem because at first we figured out that we might it might be concerning something that can be seen in an everyday context. So, and obviously part of the student group was really into physics, so we were curious to figure out a possible solution to this problem.
Thank you. Other question? Yes.
So you said that you stayed in the realm of classical physics for your presentation. It would be very interesting if you, I don't know, if you continue with the project to see what happens when you take into account the relativistic effects. And I think that there will be like very weird effects coming out of it. it could be worth a try for the next few years.
Did you hear it or?
No.
No? It's coming.
Okay.
So you said in your presentation that you left out all the relativistic effects for your stairs with no loss of energy. And I think that would be a very nice thing to look at what happens in this case. Perhaps if you continue the project, or if you don't, it could be a very interesting thing to write to the XKCD author, if you know this project. He sometimes he takes weird questions and answers them scientifically. There would be a great opportunity to see what happens in this more crazy construct of relativistic physics.
Yes, but obviously we started by taking a realistic ball, but obviously with there are a lot of problems concerning a realistic environment, such as the possible deformation of the ball itself, or the initial velocity that must be more than 1 than 0, as we consider to make calculus easier, and this little factor that obviously change in a more realistic context. And also the energetic conservation cannot be considered, obviously.
Yes. And thank you again for your nice presentation.
Thank you. Bye-bye.
Thank you. Other question in the room? No. No more questions, so we thank you a lot, and noch einmal eine super Präsentation.
Bye.